the first one, we kind of already did this. When we were adding up all the areas, we know the area is length times width, right? But did we take every number times its width? No. We added all of the heights up and then took all of that times the width. So if you have a constant times your number, you can pull that out in front of your summation. Just like with limits. If the constant isn't changing and everything's multiplied by 8, you can pull it out in front. Alright, second thing, if you are adding up a bunch of terms that have multiple components, you can add those up separately. So I can add up my A's, add up my B's, and add the final answers together. So if the thing we have is more than one term, we can add the individual terms up. So when I look at this next one, the difference is only the B has a subscript, so only the B is changing. The A is the same in every term, okay? So maybe I'm going to add up like 1 plus x squared. The x is going to change, but the 1 is the same every time. We know from the previous rule we could add up the individual terms, right? Well, if this is just a constant, you're going to take that A and you're adding it up n times. So it becomes n times A. So if you're adding up a constant, you just take it times the number of times it's added in your sum. And then we would have to use the sum for the B's. So if you're adding up 1 n times, it's just 1 times n or n.
I love this.
Good. This one's, today is fun.
Today is my day.
Okay, so now the next thing. We can talk about some rules, like how do you know that if you add up 1 through 100, how do you know what that equals without sitting there and doing 1 plus 2 plus 3 plus 4 all the way up to 100? Okay, that's time consuming. So there are shortcuts. We are going to talk about powers of I. So if I were, oops. So on this one, my base is the thing that changes, not the exponent. So it's like 1 to the k power, plus 2 to the k power, plus 3 to the k power, all the way up to n to the k power. So we are going to get formulas to add up the first few things to the first, second, and third power.
Yeah, there's a look on your face right now where you're like waiting for Carson to stop talking or something.
No, sorry. I'm making myself a note, something I forgot to do.
No, I know, but that's like the face she makes when you aren't talking. It's dumb.
Okay, so the first 3 values. If I want to add up things to the first power, so 1 plus 2 plus 3, all the way up to 100, how do we do that? Do you know what the formula is? Carson kind of talked about it yesterday. Instead of me just giving you the formula, do you want me to talk about why it is what it is?
Isn't it like
Is it the first times or plus the last times the half?
So if you think about it, if you're adding up 1 through n, so it's 1 plus 2 plus 3, n minus 2, n minus 1, and n. Would you guys agree that's the first 3 and the last 3 terms? Okay, if you add up the first and the last, what do you get?
N plus
That's n plus 1. If you add up the second and the second to last, you get
n plus
n plus 1. If you add up the third and the third from last, you get.
n plus 1.
So we get n plus 1, but it's not n times because we put them in groups of 2. So it's like half of n will be the number of times it comes up. So that's n times n plus 1 over 2. So that is the shortcut. If you are adding things to the first power, it is n times n plus 1 over 2. The next one is a little bit uglier to derive. So we can, if you're really curious, or I can just give it to you. This one is a little bit uglier. Since it's I squareds, order of operations, if you had that n minus 3 squared, you'd have to FOIL them out. So when you combine terms, it's much nastier. This one turns out to be n times n plus 1 times 2n plus 1 over 6.
Over 6.
Mm-hmm.
Wow.
Maybe that's a bonus question for tomorrow. If anybody can come to class tomorrow and prove this,
Oh, I'm so
I'll give you
down.
bonus.
I'm so
But
down.
how many bonus?
I'll make it worth your while.
Okay, I gotta prove that one.
Oh, I can do it right now.
Well, wait, because I want bonus points too. So
Okay, well then somebody could prove the IQ term
I will.
tomorrow if you want.
Is that
Okay.
easier or harder?
You guys,
I'll lock in.
I did the first one. If you guys want bonus, you can prove the second
Which
two.
one do you want?
Oh, I'll do the fourth. Oh,
Or if anybody wants to do it, write down your proof.
Okay.
Be able to explain it to you. How about that? You want bonus?
I'll do out to the fourth.
Be able to prove
Yeah.
those. And that means you can't just copy down what Google says because you have to be able to tell me what it means.
Watch a YouTube video.
Yep, you can watch a YouTube video and then be able to explain it to me. Alright, so I cubed. It's actually a lot like the first one. It's n squared, n plus 1 squared over 4. So I cubed is just the first formula squared.
Interesting.
So you need to know these. It will help you a lot and save you a tremendous amount of time. So get a highlighter, highlight this box, put a big star next to it, something. You need to know these formulas. Sorry, n squared times n plus 1 squared over 4. So the rest of today we're just going to practice using the properties in these formulas.
And you give us word problems, bad things happen to me.
What? I didn't really give a word problem.
I can't read numbers, so it really just starts me.
So find the sum of the first 13 positive integers. So I'm going to add up from 1 to 13. If it's just the integers, I'm just adding up I. So what's the formula for I?
No.
And n is my top number. So 13 times n minus 1, which is 12. Oh, whoops. I wrote that down wrong. N plus 1. I said minus. I meant plus.
I mean,
You're supposed to read my mind.
What's 13 times 14?
What did you do?
182, I'm guessing.
Okay. If notice these formulas require you to start at 1. If we're not adding up starting at 1, the formula doesn't work. So that's part of why yesterday when you were writing summations, I told you it's best if you start at 1 because our shortcuts require
I'm gonna
that.
change it to make it start at 1.
Yes. If it started at a different number, you would have to alter your I to make it match.
That's where we really breaks it. Because if it was 2,
Mm-hmm. All right, we're doing the first 13 squares. So what's the square formula?
N
Mm-hmm. And my n is
13,
times n plus 1, which is
14.
times 2n plus 1 over,
6.
what do we get?
8 times 8 times 2.
But isn't that so much faster than typing in 1 squared plus 2 squared plus 3 squared?
Oh, yeah, that's fine with me.
Alright, so the cubes. So the sum from 1 to 13 of I cubed. So what's the formula?
N squared times n plus 1 squared over 4.
That's 169 times 1. 96.
Grab a calculator if you don't have one.
8 to 11. So is the a to the 1 plus b to the 1, would that be the same as b do the same thing as a to the 1 minus, or a to the I minus b to the I?
Yes.
Because you just flip the.
Minus. Okay, let's take a look at this one. We have to use a combination of properties here, right? My shortcuts are only if I have x to a power. So first, I have to rewrite this so I'm adding up things to a power. Using my summation rules, we know if they're subtracted, we could do each one, right? So I can do from 1 to 20, 7i squared, minus the sum from 1 to 20 of 5i. Does it match my format yet? So what else can we do?
The constant one. Where you pull the constant
The,
out.
the coefficient, yeah.
Yeah, that's what I meant.
So we could take out the 7. So 7 times the sum from 1 to 20 of I squared, minus 5 times the sum from 1 to 20 of I. So let's add up I squared. I squared is n, what's my n?
20.
20 times n plus 1 times 2n plus 1 over 6. You guys know how I'm getting the 20, 21, and 41. Minus 5 times, if I add up my I, that's n times n plus 1 over 2.
Oh, I did that silly.
Should get 19,040. Definitely faster than writing that original parenthesis out 20 times and adding all these up.
Oh, it's minus there.
Oh,
Yeah,
it's 20
minus makes
it's 21, not 6 for some reason. Like I
Oh, yeah,
Not-
will
not
make
sure.
a difference.
Not really sure how I got 6, but
Do you guys think you could try one?
Sure could.
Okay.
This is like,
If you want, try the next 2 problems.
whoa, now we're kind of pushing.
I have faith in you. So this one we'll have to do the sum from 1 to 5 of I cubed minus 3 times the sum from 1 to 5 of I plus what happens if you add up 2 5 times? 2 times 5. 2 times n, which are in here is 5. Okay, the cube formula is n squared times n plus 1 squared over 4, or you could write 25 times 36 over 4, minus 3 times the I, 5 times 6 over 2, plus 10. And what do you get?
I wrote all the things you wrote.
Yeah, so
So-
you just plug something in around.
Yeah, yeah.
Probably mistyped one number, would be my guess.
Oh, I literally just wrote it down wrong.
Oh,
Anyway,
is that one okay?
are you recording? It didn't have like the little
I know,
orange
unless I
lines.
got my rectangle big.
Oh wait, now we look at this.
Alright, so if I add, I'm adding up 5 8 times. So that just becomes 8 times 5. Minus 2, if I'm adding up j 8 times, I get n times n plus 1 over 2. Negative 32.
So, the father isn't considered a constant?
It is, so that's why it's n times that. Because if you're adding 5 up from 1 to 8, that means the first time it's a 5, and the second time it's a 5, and the third time it's 5, all the way up until you have it 8 times. So you just, if it doesn't have the I in it, you just take it times the number. That's at the top of your summation.
So any constant that comes before a variable will pull out in front.
A coefficient can just get pulled out in front. Alright. Is that okay? I'm gonna do 3 more slides today. Alright, this one. My rule doesn't allow me to bring that inside a square. We don't have anything that says if it's squared, the sum can come inside. So what do you think we should do? So that would become 4k squared minus 4k plus 1. So then we do it like the previous problems. 4 times the sum from 1 to 7 of k squared minus 4 times the sum from 1 to 7 of k plus sum from 1 to 7 of 1. So 4 k squared is n times n plus 1 times 2n plus 1 over 6. K n times n plus 1 over 2. And what happens if you add 1 up 7 times? Let's see what you get.
And so how do we get that 7 over?
You're adding from 1 to 7 of 1. That means you're adding 1 up 7 times. Hmm.
455.
I got 455. Do you need me to look at it or?
Well, it's the last one we're doing today is a limit.
What?
The last one we're doing today is a limit.
Yeah.
That's not very
That's
funny.
kind of fun. All right. Are we okay with those? Let's go back to yesterday. Remember our first example yesterday? We were doing the over and under estimate for f of x equals x squared. Let's use we did it twice, once with 5 and once with 10. So let's go with the 10 rectangle. shorten up my process from then. With our underestimate. Okay, that was when we started at which number?
0.
0. Okay, so how many things were we adding up? 10. Alright, now we have to be careful. Because you said we would have to go from starting at 0, right?
You can't add 0.
So, when I'm really doing this, my formulas all require 1. When we put in a 0, it didn't change anything, right? Because 0 squared is still 0. But it has to end before the end of our thing, right? So our first rectangle isn't accounted for, it's at 0. We're actually going to add up from 1 to 9. So we're adding 10 rectangles, but the first rectangle is when x is 0. We don't want to put 0 here because then I can't use my summation formulas, but we know 0 squared is still 0, so that one didn't give us anything anyway. So we're going to add up from 1 to 9. Alright, when we did these, our change in x, we went from 0 to 3 with 10 rectangles, right? So 3 minus 0 over 10, the change in x is 3 tenths. So you're going to be adding up multiples of 3 tenths. So the first x would be 3 tenths, the next one would be 6 tenths, 9 tenths, and so on. When we added these up, we had to put them into our formula, which is x squared. So we'll be squaring them. This gives us the numbers on the inside for the height, but our area is length times width, right? What's the width of every rectangle? 3 tenths. So yesterday we were taking the whole thing times 3 tenths. I could put that out in here. Okay. So now let's use our summation rules. This is the same, saying 3 tenths, sum from 1 to 9, of 9 over 100, I squared. Or if I pull that out, 27 over 1,000, sum from 1 to 9, of I squared. So if we add up our squares, n times n plus 1 times 2n plus 1 over 6, and see what we get. Look at your notes from yesterday. What was our underestimate yesterday? 7.695. So it worked. It's hard to come up with the formulas for these, but we're just comparing that to our formulas. So let's do the overestimate.
I did not block enough space.
So it's still, the rectangles all still have a width of 3 tenths. When I figured this one up, this one started at our first one, right? It didn't start at 0, so we end at 10. And that's the only thing that changes. So that's 9 over 100 I squared, or 27 over 1,000, sum from 1 to 10 of I squared. Times n plus 1 times 2n plus 1 over 6. That's the same thing we got yesterday. If I asked you to evaluate this limit, the numerator, I am adding up 1 plus 2 plus 3 all the way to 10, or to n, excuse me. So I could rewrite that using a sum. This is a sum from 1 to n of I, because they're all to the first power. And if they were squared, it would be I squared. Or cubed, it would be I cubed. Over n squared. Okay, still hard to do this limit at this point, but don't we have a formula for what this adds up to? So if I use that formula, that's n times n plus 1 over 2, all divided by n squared. So if I think of that as n squared over 1, we can flip and multiply. What happens?
The n cancels.
So we get n plus 1 over 2n. Alright, if I plug in this infinity over infinity, what could we do?
Oh, cows.
Look at that. Derivative of the top is 1, derivative of the bottom is 2. So this adds up to 1 half. So as n's approaching infinity, this whole thing is going to 1 half.